Now that we have understood what atoms and elements are, it is important to explore how atoms exist and behave in the real world. To do this, we must understand three essential scientific terms, which are molecules, compounds, and mixtures. Let us begin by discussing molecules. A molecule is defined as a group of two or more atoms that are chemically bonded together through strong forces, known as chemical bonds. For instance, the oxygen gas that is present in the air we breathe exists in the form of pairs of oxygen atoms that are bonded together. Each of these pairs is considered one molecule of oxygen. It is worth noting that even though these oxygen molecules contain only one type of element, which is oxygen, they still count as molecules because they have more than one atom. Molecules can also consist of different elements. A common example is a water molecule, which contains one atom of oxygen chemically bonded to two atoms of hydrogen. This mixture of different elements bonded together makes it a more complex molecule. Other examples of molecules include nitrogen molecules, chlorine molecules, and carbon dioxide molecules. However, something like helium, which exists as individual atoms that are not bonded to anything else, does not qualify as a molecule because molecules must consist of at least two atoms bonded together in some way. Now, let us move on to compounds. Compounds are special substances that are made up of two or more different elements, and like molecules, the atoms in compounds are held together using chemical bonds. Many molecules also happen to be compounds if they contain more than one type of element. For example, water is both a molecule and a compound because it consists of hydrogen and oxygen atoms bonded together. Similarly, carbon dioxide is a compound because it contains both carbon and oxygen atoms. On the other hand, oxygen gas, chlorine gas, and nitrogen gas are not considered compounds because they are made of only one type of element, even though they are molecules. One of the key features of a compound is that the elements within it are always present in fixed proportions. This consistency allows scientists to represent compounds using chemical formulas that describe exactly how many of each type of atom are present. For example, water has the chemical formula H2O, which tells us that each molecule contains two hydrogen atoms and one oxygen atom. The 2 in the formula is written in subscript, which means it appears smaller and slightly lower than the letter. This notation indicates the number of atoms involved. If only one atom of an element is present, like with oxygen in water, then no subscript number is shown. Another example is carbon dioxide, which has the formula CO2 because it contains one carbon atom and two oxygen atoms. A slightly more complex compound is sulfuric acid, which is represented by the formula H2SO4. This means that each molecule of sulfuric acid contains two hydrogen atoms, one sulfur atom, and four oxygen atoms. You do not need to memorize how the atoms fit together spatially, but understanding what each letter and number represents helps in reading and interpreting chemical formulas. Sometimes chemical formulas include brackets similar to how they are used in mathematics. These brackets group atoms together, and a number written outside the bracket shows how many of those groups are present. For example, in the compound calcium hydroxide, the formula includes a bracketed group, which tells us that there are two sets of the hydroxide group and one calcium atom. This kind of grouping helps when interpreting more complex structures and helps to break down large formulas into more understandable pieces. So far, we have looked at relatively small compounds with only a few atoms per molecule. However, some compounds are made up of millions or even billions of atoms. A familiar example is common table salt, which is scientifically known as sodium chloride and has the formula NaCl. From the formula, it might look like salt consists of tiny molecules with one sodium atom and one chlorine atom. In reality, though, sodium chloride forms vast repeating structures made of billions of sodium and chloride ions arranged in a regular pattern. These are not molecules because the atoms are not grouped in fixed small units. Instead, they are part of an enormous structure formed by ionic bonds, which are strong electrical attractions between oppositely charged ions. These large compounds are still important in chemistry, but they are referred to differently because they do not exist as single molecules. In these cases, the formula does not show one molecule, but rather the ratio of atoms present. For example, in sodium chloride, the ratio of sodium to chloride is 1:1. So, if you had a crystal containing 1 billion sodium ions, you would also have 1 billion chloride ions. Finally, before concluding, it is important to touch briefly on mixtures. A mixture is a substance made by combining two or more different substances that are not chemically bonded together. This means that while the substances in a mixture may be molecules, compounds, or individual atoms, they have not undergone a chemical reaction and do not form new substances. For example, if we took a beaker and added some oxygen molecules, some sodium chloride crystals, some individual helium atoms, and a few carbon dioxide molecules, we would be looking at a mixture. This is because all these substances are simply sitting together in the beaker and are not chemically reacting with each other. They have been physically combined but remain separate at the molecular level. Because of this lack of chemical bonding, mixtures can be separated using physical methods such as filtration, crystallization, or distillation. These separation techniques work because the substances in a mixture retain their own chemical identities and do not form new compounds. These topics are explored in more detail in related videos, but it is helpful to remember that mixtures are different from compounds in that their components can be separated relatively easily without changing their chemical structure.